So far we have discussed qualitative characteristics and properties about solubility in solutions, but we haven't discussed anything quantitative. So we are going to start calculating things, specifically concentrations. So this particular video is all about concentrations and converting between them. So if you don't have your calculator out, search for it under that big pile of homework or in your backpack, wherever it is, take it out. So first we have mole fraction. So mole fraction is the ratio of moles of a substance to the total number. So all it is, keep it simple in your head, is moles of a component over the total moles of all the different components. So it's a part over a whole. Now, the good thing about mole fraction is it's independent of temperature. So temperature doesn't affect this value. We can calculate mole fraction for both the solute and the solvent, and whenever we calculate these two, they should add up to 1. And this is the actual like basic equation for this. Next we have molarity and molality. So I made a small mistake right here, so just keep that in mind. That's supposed to be molality. But molarity, this is a review from something you learned in Chem 1. So we did introduce this in Chem 1. The symbol is a big M, capital M, and we define it as moles of solute per liter of solution. So the limitation, so like the downside to molarity, is the fact that molarity is temperature dependent. So if temperature changes, the volume will change. And if the volume changes, it changes the denominator, which overall changes the value of molarity. So you can see how it can fluctuate because of volume, because of the temperature. Now molality is moles of solute per kilogram of solvent. We denote it with a small m, a lowercase m, and it's independent of temperature the same way that mole fraction is. So that's the upside to it. So it's moles of solute over kilograms of solvent. So there is a general process that you can follow to convert between these units, and we're going to use this as we are practicing. And before we go into practicing, I do want to show you the units and compare how these look. So molarity, the units will be mole per liter. Anytime you see molarity stated like that, because you can say, okay, something is 0.5 molar, you can just write it like that. But know that this is equivalent, the big M is equivalent to mole per liter. In the same way, M for molality is equivalent to mole per kilogram. And something interesting for mole fraction is that there is no unit for mole fraction. The mole cancels out for mole fraction. The rest of these, I just have them here along with this table. You can check them out. I, for example, if you took Chem 1 with me, I do teach these different units in Chem 1. It depends on your professor, but we're not going to really use them for now. So in this example, we will be both calculating mole fraction and also molality. So it's a bit of a long problem because we have to calculate both. So that's why I zoomed out, because I'm going to need space. So the antifreeze in most auto radiators is a mixture of ethylene glycol and water with minor amounts of additives. What are A, the mole fraction, and B, molality of ethylene glycol in this solution prepared from this amount of glycol and this amount of water? So first, we are going to calculate the mole fraction. Mole fraction, just to remind you, is moles of a component over total moles. So we are going to calculate the mole fraction of ethylene glycol in this solution. So to do that, we first have to calculate moles of ethylene glycol, and I'm just gonna abbreviate it. And we also have to calculate moles of water. So to do that, we are going to take the mass of ethylene glycol, which is 2.22 times 10 to the third grams, e.g., just to abbreviate. And then I will use the molar mass, which is 62.07. If you're wondering where I'm getting the molar mass, you can either add it up based off of this formula, or you can Google it. And then this gives me 1 mole of Eg. And you should get from this 35.8 mole. For water, we're starting off with 2.00 times 10 to the third grams H2O, right? And then we are using the molar mass of water. This one's a bit easier. It's about 18. That's what I use. I'm approximating it. This gives me 1 mole of H2O. And remember to cross your units out. From this, we should get 111 mole H2O. So now we are ready to calculate the mole fraction of ethylene glycol. So the notation for mole fraction is this squiggly X. That's how I like to say it. And we're going to calculate it for ethylene glycol. So we are going to take the moles of ethylene glycol, which is 35.8 mole. And then we are going to add up the 111 plus this 35.8 mole. And that will give us our total. So whenever we add this up and calculate it out, you should get 0.244. Now notice that the units cancel out, so the mole fraction for ethylene glycol in the solution is 0.244, no units. Next, we are going to calculate the molality. So I'm going to square this off. To calculate the molality, we need the moles of solute, and we are going to divide these by the kilogram of solvent. So the problem in this case told us that ethylene glycol is what we're searching for. So they're asking about mole fraction and molality of ethylene glycol. So that's why we are considering ethylene glycol as a solute. So we are going to take the same mole that we calculated for ethylene glycol up there when we were searching for the mole fraction, and we're going to use that. So you don't need to calculate that again. So we have this. What we need is the kilograms of solvent. So we're going to take the grams of water that we started off with, grams H2O, and we are going to convert it to kilograms. So in 1 kilogram, there is 1,000 grams. You could also write it as 10 to the third grams, whichever one you want. From this, you should get 2 kilograms of H2O. So now we're basically ready to calculate the molality because now we have the kilogram of solvent also. So to calculate the molality, we're just going to plug and chug 35.8 mole divided by 2 kilogram of H2O. So whenever we divide this out, you should get 17.9 molality. So we figured out both the mole fraction and the molality for ethylene glycol in this solution. So in this example, we are converting mole fraction and molal concentrations. In the previous example, we were given, straight up the masses, the starting masses of both the solute and the solvent. In this case, we are starting off with a certain concentration, and we are going to convert it to the other 2 concentration types. So that's why I have this little guideline here, the one from earlier. So your first step should be to write the given concentration as a ratio. So in other words, you're going to translate what molal actually means. So 3 molal also means 3 moles of solute over 1 kilogram of solvent. That's our first step. Next step is to separate into the solute part and the solution part. So basically just understanding that we have the 3 moles of solute and we have 1 kilogram of solvent. And next, depending on what you're converting to, will dictate which of these steps you actually need. Some of them you won't need it. So for example, we are taking this Malal to mole fraction. So we know that we already have this in moles, so we don't need to convert the moles of solute to anything else. We need to convert the solvent to moles. So remember, mole fraction, and in this case we are referring to sodium chloride, so I'm going to write NaCl, will be the moles of NaCl, in other words our solute, over the total moles of both the solute and the solvent. So we need to convert the solution or the solvent part into the required unit. We don't need to do this one because it's already in mole. So we need to convert that 1 kilogram. Now, what is that 1 kilogram? So anytime you have a solution with an ionic compound such as this one, it will be, the solvent will be water, okay? So it's 1 kilogram of H2O. So first we're going to convert this to grams. So in 1 kilogram, there is 1,000 grams. And then we will use the molar mass to get to moles of H2O. So 18 grams of H2O gives us 1 mole of H2O. So all that cancels out. And then we should end up getting moles. Now you should end up getting 55 mole of H2O. So we get those moles of H2O, and now we can finally calculate the mole fraction of sodium chloride. So for sodium chloride, we would take the moles of sodium chloride, which is 3 mole. You don't really have to specify the type of mole because it ends up canceling out. You don't have a unit, so you can just say mole. And then for the bottom, we're going to take 55 plus the 3.0 total mole. So it'll end up being 3 divided by 58. Now what you should get from that is 0.052. So our mole fraction for this sodium chloride is 0.052. So here we have an IV infusion of this molarity aqueous glucose with this density. It's part of post-op recovery therapies. What is the Malal concentration of this glucose in the solution? So we're going from molarity to Malal. So let's look at what is similar between molarity and what is different. So molarity is moles of solute over liters of solution. So SOLN. Malal is moles of solute again over kilograms of solvent. So here, the mole on the top is the same, so we don't need to convert that. But the liters to kilograms, we do need to convert. So we started off by writing it as a ratio, we separated the numerator and denominator, and now we are converting the ones we need to, and we figured out that the solute part we don't need to do. We are on this part in order to calculate the new concentration. So we are going to start off with our liters, which is, and let me just write this out first. So we have 0.556 moles of glucose in 1 liter of solution, right? So we need to take this liter of solution to kilograms of solvent. So to do this, we're going to start off with our liter, and then we are going to convert this to milliliters. So in 1 liter, we have 1,000 ml. That's an L. And then next, what we can use, and this is why they gave you the density, we can use the density to get to grams. So it ties it all together. So in 1 ml, per every 1 ml, we have 1.04 grams of glucose. And that cancels out. And now we are finally at grams. Now at grams, we can convert it to kilograms. So 1,000 grams is 1 kilogram. And finally, Oh, this shouldn't be glucose. This should be solvent. I'm sorry. But finally, we're at our endpoint. And what you should get is 1.04 kilograms. So now we have our mass of solvent. Well, solution actually. So that's actually that brings up a good point. So this is of solution, right? It isn't of solvent by itself. And it's easy to, just kind of automatically write it off, just how I was about to do, and just say, okay, this is the solvent by itself. But in reality, it's not. So there's a little step we have to do in order to get the true amount of solvent. To do that, we are going to take the moles of glucose and we are going to convert it to a mass. To do that, we are going to take the molar mass, which is in 1 mole of glucose, we have 180.2 grams of glucose. Okay, this gives us 100.2 grams. In other words, 0.1002 kilograms. Okay, what we have to do is subtract those kilograms of out of that solution so that we can get solely by itself the kilograms of solvent. So you're going to take the 1.04 kilograms of solution, subtract that 0.1002 kilograms of glucose in there, and then we will get how much water we have, which is 0.92 kilograms of just H2O by itself, in other words, the solvent. So now we can finally get our molality. So we will take, so this was getting the kilograms of solvent. This was getting the mass of our solute out of our solution. And then finally, we're on calculating the molality. So we will take the moles, which is 0.556 mole, divided by our kilograms of solvent. And from this, you should get 0.60 molal. So this is also something you most likely learned in Chem 1, but I just want to refresh it for you. So how do we actually in lab prepare a solution? So what you will do is first you go ahead and calculate whatever you need. So you would calculate if, for example, a certain reaction is calling for, 3 molar sodium chloride, right? Or 1 molar sodium chloride, just to use that as an example because it actually is shown right here. So let's say it calls for that. You would figure out how much mass is in 1 molar of this solution, and then you would weigh that mass out. So in this case, we calculated that 1 mole of NaCl is 58.44, which is the molar mass. You would add it to our volumetric flask, which allows a very specific volume. So the way that volumetric flasks work is that they have a wider flask bottom down here, and then they have a thinner neck up here, and on this neck you will have a line. That line is exactly whatever volume this volumetric flask is for. So for example, this one is a 1 liter volumetric flask, so exactly at that line you have exactly 1 liter of total solution. So you would add in your solid NaCl, add in your water, because solid NaCl is going to take up some space, right? So then you add in your water, you mix it, you get it up to a total of 1 liter, and this gives you your 1 molar solution.